The 2D version of a moment is, again, simply the magnitude of the force times that perpendicular distance to the point at which we're calculating the moment, that rotational effect. But in 3D, it's a little more complex to write this down, and so the cross product is a much more direct way to handle the moment of a force. And so in that three-dimensional space, r cross f, when we start thinking about what's going on here, we have a position vector here from A to B. This point, note, doesn't have to be located specifically here. RAB can be defined anywhere along the line of action, and the cross product takes care of then all the little aspects of that. And so our position vector here will be rxi plus ryj plus rzk. And of course our force vector is similarly got its scalar components and its directional or unit vectors to go along with it, so that when we want to go do the cross product, we can work this out in a variety of different ways. Sometimes the most simplest direct way to do this is through a determinant type of system, where when we look at how to calculate this, that manipulation mathematically is and can be thought of as then almost, and really in essence, a determinant, where we take I, j, and k as our little unit vectors on the first row, and then we have the scalar components of the position vector rx, ry, rz, and then we have then the scalar components of our force. So arranging that into a matrix and then finding the determinant of that matrix, which there's a variety of ways to do that as well. One of the common easy ones to do is to take the first two columns and repeat them outside of our little matrix. So note, those are just the I and j components there. And then when we want to calculate the determinant, all we have to do is to then multiply along these diagonals. And so there's three of them. These are the plus diagonals. And note that when we do that, we'll get I, and then scalar in front of that will be ry and fz. And then we get a j term, and there's our rzfx, and then our k term will be rx and fy. Then that's just in one direction, and then we go in the other direction, and that's going to be ultimately the minus direction. So we'll have minus then a whole bunch of stuff, and I'm going to collect like terms right underneath each other. And so notice that the I vector component will be rzfy, and then the j term will be rxfz, and then the k term is going to be our ryfx. Note that in every case that in a sense the subscripts are all different. There's no repeated subscripts. Y, x, k. Well, k is not a subscript, it's a unit vector. But x, z, j, z, y, i. You always have unique mixes here, right? And notice then too how these stack up: rx, fy, and then we get ry, fx, right, with a minus sign. Right? So there's always that mix going on and that pairing as well. And when you start looking at it that way, some people will recognize, and long time recognize, that a way to think about this was to take our unit vectors, I, j, k, put them in a triangle, put them in a counterclockwise sequential pattern, because in the right-hand rule system, counterclockwise is positive, right? So when I go around the circle in a counterclockwise fashion, it tells me that I cross j is equal to a plus k, whereas if I go j cross I, it's equal to a minus k, right? Again, so that just means that the vector, instead of being this way when I do that product, is completely turned around, right? And so that allows us to do the math manipulation in another way, which is way back up here at the beginning. Instead of doing the matrix approach, sometimes it's actually more convenient to work this out longhand, especially if you have zeros that are populating certain aspects of the position vector and of the force vector, right? So you'd have rxi plus ryj plus rzk cross, and then the force vector written as fxi plus fyj plus fzk, and now we can apply our basic commutative type rules or associative or distributive type rules for cross products. Then I'll take this first part of the one term and I'll cross it with all the individual parts in the second one. So recognize we'll get rx sub I cross fxi, but I cross I is 0, so bam, it goes away, right? Ooh, wow, because that's because we never see any repeated indices back up in this other version, right? And then we get rxi cross fyj, which will give us, let's see, I cross j, oh, okay, that's a k, right? So I'll write that out here, and that's rx times rx times fy, so that's that one and that one, right? And then, okay, then I got one more. There's an I cross k, that's going backwards, so that's a j term, and that's going to be rxfz, but there's a minus because I was going backwards there, so minus rxfz for that j term. And that took care of all of this first term here. Now I got to do the same thing for ryj, go against I, so that's backwards, that's a minus k, so that'll be a minus ry times fx k, right? And then we get then a j cross j, that goes away, and a j cross k, that's a positive I, and so that's going to be ryfz, right? So, alright, so that got that one gone. Now we got one more to do. We got rzk cross fxi, so k cross I is a positive j, right? So that's going to be plus rzfx j. So there's all our j terms, right? And then we've got k cross j, that'll give us a minus I, so we have a minus rzfx, right? And I don't want to put the brackets over here because I don't want to put a minus sign just quite like that. Just leave it just like it is. But notice this is going to be ultimately the exact same expression that we had right up above here. These two are identical. Two different ways to do it. If I had fully populated vectors for both r and f, I would do the determinant approach, but if I didn't, I would probably do it this other approach, because a whole lot of these would disappear because they have a zero scalar magnitude.